This is inclined planes part 2. Well, we're going to set up a question where we actually are applying a force on the inclined plane and we're trying to lift something up a ramp. So let's draw a little picture. Let's say we have a ramp, something like this. And the ramp will be, I'm going to make this a fairly large angle, 60 degrees. 60-degree ramp. I know it doesn't look like 60, but that doesn't really matter as long as we follow the numbers. Let's put our mass here, and let's make this a 100-kilogram mass. Let's add in a coefficient of friction. The mu will be 0.2 this time. And the question that we're going to ask is, how much force is required to slide the box up the ramp at a constant speed? Because that's how we usually pull things. We don't usually push and pull things around, making them accelerate. Often we slide things around. Oh, let's spell it right. Constant speed. Okay, first thing we will do is draw our free body diagram and put in all the forces that we can think about here. So we'll start with our gravity force, which is always straight down. So there's our force of gravity. I'll put Fg here. And if we want to, we can go ahead and calculate that, because we know that the force of gravity is mg for 100 times 9.8, which in this case is 980 newtons. So we actually know the number for the force of gravity. Other forces we'll need to consider are the normal force, and remember that it has to be perpendicular to the surface. So it points off in this funny direction, Fn. We are applying a force up the hill. If we're trying to slide the box up the hill, then our applied force obviously needs to pull up the hill. So this we'll call F applied, and this is what we're after. This is the force required to slide the box up the ramp. The only other thing we have to label is our friend force of friction. If the block is going to be pulled up the ramp, the friction would oppose that motion, and so the frictional force is going to act this way. Friction doesn't always have to act in the opposite direction of the applied force, but in this case it does. So we'll put it like that. Now what we're going to do is take our little trick that we learned. Remember we said if we take our reference frame and we just twist it over a little bit so that it looks like this, it will match the ramp. And the x-axis becomes the surface of the ramp, and the y-axis becomes perpendicular to the ramp. So vertical now means along the y-axis, or perpendicular to the ramp, and horizontal means up and down the ramp. The beautiful thing about this is 3 of our forces, the friction, the normal, and the applied, are all entirely on one or the other. The normal is all uppy-downy, while the applied force and the frictional force are both lefty-righty forces. Gravity, though, is at a funny angle now. It's no longer on one of the reference lines. So we have to do the other trick that we learned, and we have to resolve the gravity components to find out how much of the gravity is pulling down into the slope this way, and at right angles to that, how much of the gravity is pulling down this way parallel to the slope, right angle here. All right, I'm going to have to switch to a smaller pen, I think, because otherwise it's going to get nuts. Okay. The side of this, we've already seen that inside of here, in the previous video, we saw that this would be 60 degrees, and how we showed that. So I'll just put the 60 degrees in there. You can play with the trig. Basically, this is 30, and then the whole thing is 90, so it makes another 60, and it works out the same as the angle of the incline. That means that this side is called FG X. This will be the X component. Sorry, that's my mistake. It's Y. Let's erase that. FGY, the Y component. And it will be equal to mg, force of gravity, over here, times cosine of 60, which is equal to, in this case, 980 cosine 60. Cosine 60 is a half, so half of 980 is 490. So this will be 490 newtons. That's how much of the gravity is pulling down into the slope. On the other side here, we have FGX. This is the horizontal component, the amount of gravity pulling down the ramp. And it would be equal to mg sine 60, because it's opposite to the angle that we're using. And then we would have 980 times the sine of 60, which is 0.87-ish, I think. So what does that come out to?
814.
814.
48.
Sorry?
48.
848?
Yeah.
Well, we'll erase it. We'll just kind of fix that up. 848 newtons. So what we've done is we've discovered how much of the gravity is pulling into the slope over here, and how much of the gravity is pulling down the slope. Now we're ready to do our F net X and Y's and see if we can't come up with an answer. All right, we'll start with F net X. No, we'll start with F net Y. It doesn't matter, but usually starting with the Y gives you a little bit of extra information. If in fact you start with X, you'll end up with some unknowns, and you'll have to go resort to the Y anyway. We know we're going to do them both, so let's do F net Y. In the picture, there are two arrows that are up and down. Remember, the red arrow is no longer in the picture. We've replaced it with these two blue ones. So we never look at the red arrow again. We have FGY and FN are the uppy-downy arrows. So FGY and FN are the two forces in the up and down direction. If we look at this ramp, we can infer from the context that the block will not accelerate up or downwards, this way or that way. If it moves at all, it's only going to move up or down the ramp. So that means with no acceleration in the y direction, the net force will be mass times A, or 0, which is 0. The FGY is a number that we figured out. It was 490 newtons. And I also have to remember to tell the math which way that arrow is pointing, because the math cannot see my picture. So it's down, so the negative sign will make sure that the math knows which way that arrow is pointing for this 490 newtons. That leaves me with an Fn, which is still unknown, and we see what happens. 490 goes to the other side, and the 490 newtons becomes the normal force. So that'll be useful in a minute. Then, if we go down and do our F net X equation, I'll put a little line across there. For F net X, this has a little bit of extra than the example in the previous video. If you look at the picture and look for the arrows that are up and down the ramp, there are now three. There's a force applied, there's a force of friction, and there's an FGX. So we need to put all three of those in our F net equation for Y. So force of friction force applied and the FGX. And the order of these doesn't matter. If you're adding things, they can go in any order. All right. Now, here's where we have to make another decision. We know that F net is MA. So we have to look back at our original question and see if there are any hints in the context as to how this might be accelerating up and down the ramp. And what I notice are the words constant speed. So if we're going to slide the box up the ramp at a constant speed, that means there is no acceleration. And so if I go back down to here, that context allows me to write mass times acceleration. This one will also be 0 because we're sliding the box at a constant speed. You can't just memorize that and always stick a 0 in there. You have to go back to the question, look at the context, look at what you've got, and make a decision as to whether there will be any acceleration or not. But here there won't. All right, we have mu Fn for our friction, and F applied. And we have a number for the gravity. This is the x component of the gravity, which is on over here, 848 newtons. So I'll have to put that in, and I'll tell the math that it's pointing to the left, so I'll give it a negative sign as well. 848, right? 848 newtons. Okay. I think I'll just leave the ends out. I don't like putting units because they get very easily confused with variables and things get all messy. But we know if we use standard units, they'll all work out properly. Okay. We know the mu, do we not? The mu was given at the original part of the question. I think it was 0.2. So we can put that in. And we also know the Fn because we figured it out up here in the first part of our solution in the F net y, so 490 newtons. So I can put 490 here. Now, since I'm putting these numbers in for the friction, I also should tell the math not just how much they are, but which way they're going. So I'm going to go look at my picture and see which way the frictional force is going. And it's going to the left, right here. So that means I need to put a negative sign in for the friction. So I'll make the friction left. You have to tell the math which way it's going. The F applied, I don't know yet, so I'll just leave that there. But you can see what's going to happen here. It becomes the only thing left, and we can easily solve this and figure out what it would be. And so, if we calculate this number, 0.2 times 490 will be 98 newtons, right? Negative 98 newtons plus F applied minus 848 newtons. And so, if I group my like terms and move them all over to the other side, I'll have the 8, 16, 9, and 4, 13 plus 1 is 14, and 8 plus 1 is 946 newtons, equals the F applied. So that's telling me how much force I would need to pull the block up the ramp at a constant speed. Notice a couple of things. What do the terms represent? Well, this 98 negative here is the frictional force that I'm pulling against. So what I have to do with my F applied, and I'm also pulling against the gravity force of this. So my F applied, it makes sense, would have to accomplish both. It would have to pull this much to beat the friction, and this much to beat the gravity, the two things working against it. If you look at the original picture, you can see how the gravity and the friction are working against the applied force. So the math is telling us that very nicely. And that's how you can deal with a situation like this. Notice also that the applied force that you are using, if you compare it to the weight of the object, the weight of the object, mg, I believe, was 980 newtons. Was that not right? So the weight of the object is 980 newtons. That's how much force you would have to apply if you wanted to just lift it straight up with your arms. But we have found a way to lift it up, which is effectively what happens when you slide up a ramp. You get higher for a force of only 946 newtons. We've done it cheaper, less effort. It sounds like we've gotten something for free, but we didn't. If I go back to the picture, I'll show you where the trade-off is. And this picture's pretty messed up, but I think I can show you over here. This is the height of the ramp, and we have lifted up. We would have to apply 980 newtons to lift straight up like this. But instead we used 946-ish, but look how much further we had to push the object. So we used less force, but we had to slide it over a greater distance. And if you recall from your last year, work equals force times distance. And so we've actually done, the amount of work that we've done is not necessarily the same, but we use less force, and that's what we're after when we use a ramp. Because humans are fairly weak when it comes to the animal kingdom, so we are looking for ways to use less force, and the incline plane is one of the things that does that. It allows us to trade force for distance, and it's a simple machine that does that. And that's the end of that.